Hello class, we're team number 9. Team members are Valeria, Proano, Camilo, Trujillo, and myself, Ruocco. Today we're going to talk to you about the 4-bar mechanism and the slider crank. The 4-bar mechanism is the most simple attached linkage. It is composed of 4 bars or links that are held together by revolute joints. Usually one link is fixed. This is called the ground or fixed link. The 4-bar mechanisms are most preferred machine components in the industry due to their large number of applications. The type of 4-bar mechanisms are the crank rocker, which is when one of the links is the shortest, is attached to the base. The double crank is when the base is the shortest link. The slider crank, which has a rotating crank, a link, and a slider. And the double rocker, when the coupler link on the top is the shortest link. Now Valeria is going to talk to you about the procedures.
The procedures for the analysis of the 4-bar mechanism are as follows. The position equations for the theta 4 input, we're going to solve with this theta 2 and theta 3, which are the positions of link 2 and 3. Then we're going to calculate the trajectory of S with theta 5, and we're going to go to the velocity equations for the omega 4 input. We're going to solve for values of omega 2 and omega 3, and then we're going to go for the acceleration analysis with the alpha 4 input. We're going to solve for alpha 2 and alpha 3, and all of these analyses are going to be evaluated for a complete 360 degrees with a 1 degree step. These are the equations that were used for these analysis. You can see the position equation, the velocity equation, and the acceleration equation. The velocity equation is derived from the position equation, and the second derivative is the acceleration equation. These are the matrices and the position equations that were used. Now, Camilo is going to talk to you about our mechanism and our application.
How you doing, guys? As you can see over here, you can see our basic 4-bar mechanism with the trace on the upper link and the lower link. This is the actual SolidWorks of our application. We actually have a video for the application. Let me talk to you about our application. Our application is basically the Morgan paddle wheel drive, which is a system that contains a linkage that moves paddles through a given angular orientation. This is basically used in steamboats and some other water applications. A modern application for this type of system is helicopters. Now I'm going to talk to you about some of the conclusions for a 4-bar mechanism. We perform a full mathematical analysis for the 4-bar mechanism with the given angles and linkage given by the project. We analyze the motion, the input joints, and divide into 1 degree steps in order to get 2 closures and analyze them. Furthermore, we get the position trajectory, the attached copper link, and the junctions for link R2 and R4, which was determined. Now we're going to talk about the slide crank.
Okay, so the slider crank. This mechanism basically converts rotary motion into linear motion and vice versa. The slider crank is widely used in engines to convert the linear thrust of the piston into useful rotary motion of the driver shaft. Also, the slider crank mechanism is found in human power. Basically, when you're riding a bicycle or you're operating a drilling machine, your arms are going to be a simulation of a slider crank. Now Valeria is going to talk to you about the procedures.
The procedures for the synthesis of the slider crank mechanism are a little bit more complicated. First, we got 3 positions for A and B. We did the 3-point circle equation, and that way we found R2 and the length of AB. With that, we found the pole position for P12, P13, and P23. With P23, we were able to find the image pole position, P23 prime. Then we went for the circle of slides and the radius. With this circle of slides and radius, we picked a point, which was going to be our C, and we calculated the local X and Y for that point. Then we went with those 2 lines from local to global to find C2 and C3 and make sure that they were in a line, C2, C3, and C1. Then we calculated theta 1, theta 4, R4, and R3, and we used our theta 2 as input for the position equations to make sure that our system wasn't locking up. And that way we obtained R1 and theta 3. These are the equations that were used for this analysis. We have the circle passing through 3 points, the pole position, the image pole position. Then we have the local to global coordinate and the local to global and the global to local. And these are the matrices that were used. Now, Camilo is going to talk to you about our application and our mechanism.
Basically, for the slide diagram, we come up with this kind of configuration. Basically, we give the configuration, the application for a plower. A plower is basically a mechanism that is used in the agriculture industry. What it does is basically turn over the upper layer of the soil and turn it so the bottom of the surface comes up and it brings nutrients for future planting. As you can see in the animation, the bottom part actually takes out the surface and move it so be able to rotate the soil. Now I'm going to talk about some of the conclusions that we come up for the slide diagram. To begin with, they were given to us a coordinate of points provided by the instructor. The problem that we have with those points is that restrict the mechanism from rotating a full 360 degrees. In order to fix that problem, we adjust our copper links plus or minus 1. In order also to make it work, we make some changes to the selected angles of each perform in order to assure that the mechanism actually rotate a full 360 degrees. Basically, this is what we come up for both projects. Thank you, and see you guys later.